Okay, so let's take a look at how we can use this idea of Fourier transforms for some of our building block signals that we looked at way back at the start of the course. So we'll start off with a rectangular pulse, and I've just put the Fourier series and Fourier transform and inverse Fourier transform up in the corner for reference. So if we have a rectangular pulse, we know it looks like that. That's clearly a non-periodic signal. But if we just go straight to this definition, let's see what we calculate for this integral. So although we're supposed to go from minus infinity to infinity, this signal is only non-zero over the range minus tau over 2 to tau over 2, and it's got an amplitude of a. So we just stick that straight into the integral, and then if you do that integration, and you'll get this at the limits, but I'm going to multiply by 2 over 2. The reason is because I already know that this is going to be a sinusoid from Euler's formula, and I need that 2j on the bottom to make it that sinusoid. So we get sine omega tau over 2, and you'll notice it's over omega still. So now I have a something like sine omega over omega, and that is a sinc function. So I've just made the arguments the same, and then we get a sinc function. So graphically, the spectrum of the Fourier transform of, the spectrum of x, which is the Fourier transform of x, is a sinc function. And you'll note that in terms of frequency, not omega, but actual frequency, those zero crossings are at 1 over tau. So you give me any pulse width, and that will tell you where the zero crossings are. This is probably one of the most important signals because a lot of our modeling of digital type applications assumes pulse-like signal shapes. So you have a pulse for on, and then when it's 0, it's off, so representing 0 and 1. So if you have a binary bit stream, this is a good way of representing it. It's also the type of signal that's used for if you modulate with, for instance, like a radar signal. So it's turned on for a certain amount of time and then turned back off again. Okay, another important one is the unit impulse. So in the time domain, we just have the unit impulse, and if we go straight to the definition and try and figure out what the Fourier transform of that is, remember that by definition, this impulse function under the integral returns you the value of this, in this case at t equals 0, wherever the impulse is. So at t equals 0, that exponential just becomes 1. And so that's from the sifting property. So what does the spectrum look like? Well, it's just a constant. I just want to return to that for a second. So think about what that is saying. It's saying that an impulse function has frequency content that is the same for every single frequency, and every single frequency is in it. Let's take a look at that unit impulse function again, but with a little bit more insight. So remember that we defined the unit impulse as the limit of a pulse function. So a pulse function that had a width of a and a height of 1 over a, or amplitude of 1 over a. That way it has an area of 1 all the time. Remember, we took the limit as a went to 0 of that. So if we already found the Fourier transform of a pulse function. It was a sinc. So the Fourier transform of q is just a sinc function. And now if we take the limit as a goes to 0, what's the limit of a sinc function as a goes to 0? Well, it just becomes 1. So when a is 0, it's the value of sinc at 0. It's just equal to 1. So if you take a look at spectrally what's happening, so in the frequency domain, as a is getting smaller and smaller, we start with a sinc function and we get wider and wider sinc function, then eventually it just becomes a flat line equal to 1. Okay. Another important one is a one-sided exponential. You've already seen that in other classes that this is, for instance, the response, the impulse response of a RC circuit. So let's take a look at the Fourier transform of this. Now we only need to take the limit from 0 because it's 0 before that. And it's just the integral of an exponential evaluated at the limits, and you just get 1 over a plus j omega. What does that look like? Well, now we have a complex valued spectrum. So it has both real values and imaginary values. And so we want to plot it with both amplitude and phase. And note that the spectrum sort of is, the amplitude spectrum is even, of course, and it looks like a big bump. And then the phase looks like this, where it's approaching 90 degrees at minus infinity and minus 90 degrees at positive infinity. And there's this section in between, which is sort of linear. And we're going to remember that in a little while. Or you might actually take a look at that in your circuits class. Okay, let's think about a complex exponential. So this is really just, what is the Fourier transform of a single frequency component? That's one way of thinking of it. So remember, a complex exponential has both a real and imaginary part. In other words, a cosine and a sine. Or if we represented it with magnitude and phase, it has a constant magnitude and a linearly increasing phase. If we go straight to the definition of the Fourier transform, oh, I've given it an amplitude of a here, it doesn't really matter. If we go straight to the Fourier transform, we take a look at that. Now the problem is, if we do that integral, that exponential, we're going to get that exponential over j omega naught minus omega, but we have to evaluate that at minus infinity infinity, for t equals minus infinity to infinity. Well, who knows what that value is? We really can't calculate it that way. So let's think of a different way to do it. So we know, let's take a look at the reverse. So if we knew what the Fourier transform was, we need to be able to recover the original signal from that integral for the inverse Fourier transform. Well, take a look at that. It's giving me an exponential at a certain frequency. So a good guess is that we can think of that sifting property of the impulse function, that if I put an impulse at omega minus omega naught, I should sift out the value at omega naught. And we need that 2 pi to cancel this, so let's just take a guess. Yeah, so by the sifting property, we would recover the original signal. So that's to say that our guess was correct, not surprisingly, because I knew what to expect. But this is just saying that the Fourier transform of a complex exponential is an impulse, and it's an impulse sitting at omega naught. Now, if we know that result, we can also figure out what the spectrum of cosine and sine look like, or the Fourier transforms of cosine and sine. So remember that cosine and sine are actually periodic signals, but we are finding Fourier transforms for cosine and sine. So what we're seeing is that we can actually use the Fourier transform in some instances to find the Fourier transforms for periodic signals. So not just non-periodic, but also periodic. So we can go straight to Euler's formula for cosine, and it's just 2 separate complex exponentials. And so the Fourier transform looks like this. And if we graph it, the amplitude spectrum would look like that. Sine function is just slightly different, and you'll notice that the amplitudes are now minus j pi and j pi. So the amplitude spectrum would actually look the same. Why is that? Well, because the only difference between cosine and sine is that they are 90 degrees in phase apart. So although the amplitude spectrum looks the same, the phase spectrum will actually be different. So that was an example of how we could find the Fourier transform of periodic signals by using this idea of the complex exponential. So how can we extend that to any periodic signal? Well, any periodic signal has a Fourier series. And if we wanted to find the Fourier transform of that periodic signal, we can stick that expression for the Fourier series into the integral definition of the Fourier transform, and then reverse the order of integration versus summation, and then this is what we just solved. So we already came up with that answer right there, and so the total Fourier transform of any periodic signal just looks like this. So we can find the Fourier series coefficients for a periodic signal, then the Fourier transform is just given by a bunch of different impulses that are multiplied by 2 pi times that Fourier series coefficient. So this gives us a way of how to go from a Fourier series spectrum to the Fourier transform spectrum. So you'll notice that every coefficient is being multiplied by 2 pi, and we're no longer graphing against k, we're graphing against omega naught. Or sorry, graphing against omega.